Well, today it's a particular pleasure to welcome this afternoon's speaker, Feryal Ozel. She's a noted astrophysicist from the University of Arizona. She's actually in Aspen these several weeks as a co-organizer of a research workshop on the properties of neutron stars. These are stars roughly the size of Aspen, but weighing as much as the sun itself. Originally from Turkey, Feryal was educated at Columbia University and the Niels Bohr Institute in Copenhagen, and then received her PhD from Harvard University. She was then a postdoctoral fellow at the Institute for Advanced Study in Princeton, eventually joining the faculty of the University of Arizona in 2005. She not only works on theoretical aspects of astrophysics, she's been very involved in taking data. For example, starting a quite remarkable program of measuring the masses and radii of neutron stars. They're all about 15 miles across. And then deducing how strong the matter has to be in the interior in order for the stars to be the size they are. Her talents have been well recognized for example, by the Maria Goeppert Mayer Award of the American Physical Society, by the Bart J. Brock Prize, just to name two. She's also well known for her public service, serving on NASA committees, and frequently appearing on various television documentaries, as well as writing many popular science articles. So today she'll talk about the Event Horizon Telescope, which aims to peer into the immediate vicinity of black holes, including the one at the center of our galaxy, the Milky Way. So let's welcome Feryal to talk. Please.
Thank you, Gordon, very much for that lovely introduction. And thank you all for coming on this beautiful Aspen day to hear about black holes and this ambitious, or one way to look at it, or crazy worldwide experiment that I'm going to tell you about, taking the first ever picture of a black hole. But before I tell you why we're doing this or how we're doing this, we should talk a little bit about black holes. What is a black hole? And before I can do that, we should talk a little bit about gravity, because really black holes are the most bizarre things that are in the universe, most bizarre gravitational objects that are in the universe. So let me begin by telling you a little bit about our theory of gravity, how we understand it, and then go on to black holes and the Event Horizon Telescope experiment. Of course, no gravity talk would be complete without showing a picture of Einstein. In this particular case, it's not a gratuitous picture. I really am going to tell you about general relativity, the theory of gravity that we hold dear today. But Einstein is not the only person, or is not the first person who told us about gravity. Of course, our understanding of gravity goes back to Newton, who formulated it as an attractive force between two objects that have a mass. And Newtonian theory of gravity did extremely well. It explained a lot of things about the solar system. It explained gravity that we experience on Earth. But it wasn't compatible with relativity. So Einstein's first theory, special relativity, how objects move with respect to one another. So Newtonian theory wasn't compatible with that. And furthermore, when you look at the motions of planets, the innermost planet, Mercury, precesses, because it has an elliptical orbit, its orbit actually precesses in its axis around the sun. Newtonian gravity could not explain that. So Einstein really started rethinking in a very deep way about what gravity is, and reformulating what it is that objects experience and what it is that space-time experiences when they interact with one another. So he said, actually, there is no such thing as a gravitational force. Gravity is a geometric theory in the sense that any object that has a mass has an effect on its surrounding, that surrounding in particular being what we call the space-time, and I will show you an example of that. And that most objects just interact through this bending in the space-time. So he gave us the tools, really, that we use to think about gravity today. So in particular, what he said is the following. Let's say this is our sun, and this fabric right here represents space-time. So think of four people holding four corners of a blanket, and you put a heavy object in the middle, And you know extremely well that that curves that blanket and kind of sags. So what he said is space-time is no different. When you put a massive object, it actually just kind of curves the space-time around it. So now let's think about what happens to an object that is near it. So now take a marble and go from one corner of that blanket and let it go. What is it going to do? It's going to go straight into that, that curved part of the blanket, right? So what he said is that objects and light alike just take straight paths in this curvature of space-time that is created by another massive object. And that's all there is to it. It just follows like an ant walking along, and let's say it comes on a bump. The ant doesn't know that there's a bump there. It just keeps going straight, climbs over, and comes back down. So that's what light does. Now, when I say straight, I put it in quotes because this may not look straight to us, but let's say that there is a star. This is us on Earth. This is our sun. Let's say that there is a star behind our sun. Normally, of course, the light from the sun would completely overpower the light from that star. We wouldn't be able to see it. But let's forget about that for a second. What would happen to the light emitted from that star is that it would go along its merry way, just like that ant, go in and climb back out and reach us on Earth here. But because we don't know exactly where it came from, we would see it coming this way, and we would extrapolate it, and we would say that the star is here. This is called gravitational lensing. It's called lensing because a lens does exactly the same. It bends the paths of light so that things behind it look a little bit distorted, right? Even a glass of water will do that. Yeah. So what Einstein predicted is that if we could see the actual position of a star when the sun is not there, and compare it with the perceived position of the star when the sun is there, that we would see a difference because of this gravitational lensing effect. Okay, pretty bizarre, right? So he made this prediction in 1915. It wasn't until 1919 Sir Arthur Eddington took an expedition off the west coast of Africa. And what they were after, of course, was a solar eclipse, just like the one that we're about to experience in August here in North America. So they chased the eclipse, and the reason was that if the sun is eclipsed by the moon, then momentarily we will be able to see those dim stars that are normally behind the sun. And what they did was they compared those positions with those taken 6 months before when sun was in the other part of the sky. So this is an original picture, that's why it's very hard to see, I apologize, but I will point out to you what it is that you're supposed to be seeing. So there are these tiny dashed lines here and here, here and here. These are pairs. So one shows you the actual position of the star, and the other shows you the perceived position of the star when the sun is there. This was, of course, a huge triumph for Einstein. It actually proved that this geometric theory of gravity works, and people were completely going crazy all over the world. This is a New York Times cover from November of 1919. Really, lights all askew in the heavens, and Einstein theory triumphs. And of course, it goes on to say, no more in all the world could comprehend it, said Einstein. He didn't say anything like that, but for example, Eddington actually knew exactly what he was looking for. Anyway, so this now becomes the new standard for our understanding of gravity, why things fall, how bodies in the universe attract each other, and how light behaves around them. So there is this concept of gravitational lensing that is quite important for our observations in the universe. For example, we see very strong evidence that this is happening when we look at galaxies that are behind galaxy clusters, or when we look at other objects that are behind massive objects in the universe. what you're seeing here is an iconic Hubble Space Telescope picture. So these arcs that you're seeing, these blue ones as well as these arcs that you're seeing, all belong to a single object that is behind this massive galaxy cluster. So it just happens to be in our line of sight, us, this massive galaxy cluster, and this other galaxy behind it. And because of this curvature of space-time and how light follows it, we are seeing many, many, many different images of it, all the light lensed around it and reaching us. So you see also pieces of arcs everywhere here. So it's something that we've seen many examples of in astronomy. So you might now think, great, how does this connect to black holes? Well, black holes are nothing but the most extreme gravitational lenses that the universe makes. There are many different descriptions of black holes. This is the one that makes most sense to me, because what they really do is they pack so much mass in such a small volume that all the paths around it of matter, of light, of anything that comes in their vicinity is bent inwards. So not only do they curve it around them, they curve it so much that it actually comes back inwards. So I call them the ultimate gravitational lens. And what that does is it creates what we call an event horizon. So basically a surface, a sphere, beyond which we have no access to light, to what objects do, if something falls in, what happens to it, what its fate is afterwards. Okay? So if we believe Einstein's theory of gravity and that it works, even in this bizarre prediction that it's making, that the universe creates such high densities of matter that it curves all the light inwards and it creates these pockets from which we can get no information, no light, then we should be able to find signatures of that event horizon by looking for black holes in the sky. So just for fun, I will show you this animation that is actually done with correct physics. Our trajectory, as if we're falling into a black hole, is shown in white here. We're going around. The red is the event horizon. This is a grid. Obviously, you wouldn't see it if you were falling into the black hole. Nobody would paint a grid there. But just for you to see how space is distorted. And this is a clock running slower and slower, which is what would happen if an observer outside of the horizon would be looking at you. And now we're about to cross right here. And you see that now all the light, not just the grid that represented the space ahead of you, but now everything that is all around you has collapsed to one single place. So at that point, once you cross the horizon, there is no such thing as your back, your front, your sides, etc. Everything is now pointed towards the center of the black hole. At least that's what we think. Nobody actually did this and sent us a picture. So, but this is what we imagine, physics-wise, is happening inside of the black hole. So, since we can't send somebody there, not even a graduate student who might be willing to do it for their PhD, what's the next best thing we can do? We can try to take a picture of it, but what would we see? So I'm describing to you something that is so powerfully pulling everything towards it that it's black. That's why we call it a black hole. Well, what we would see is, as it's shown in this diagram from the 70s when black hole research was really taking off. Let's say that this is our black hole. This is someone kindly shining a light on it, standing behind the black hole. Let's say we are here. What we would see is that some of the rays just grazing the black hole, actually appearing as a light ring here. And anything else that is falling into the black hole appearing black. Okay? So if we did have a source of light that was shining onto the black hole, we would see a silhouette. we would see a ring of light around it, and inside it there would be an actual blackness. Okay? Obviously, nobody's holding a flashlight for us on a black hole either, but luckily they don't have to, because black holes are actually very interactive with their environments. If a gas cloud or a star comes a little too close, their paths will also be bent inwards, and the black hole is going to start sucking them in. And when that happens, the temperatures are high enough that that gas starts glowing and emitting light, coming from all around the black hole. Okay? So even though we don't have this situation where we have a flashlight, we actually have natural sources of light coming from around the black hole. And just like this bright ring forms right around it and punctuated by this utter blackness, what we expect to see is this bright ring forming around the black hole, punctuated by this blackness, this silhouette, shadow, whatever you want to call it, in the middle. Now, is there a difference between this ring on the left and that ring on the right? Probably most of you are seeing it, that this one actually does not look like a symmetric ring, right? It looks more like a moon. It looks like a crescent. It's brighter on this side and less bright on that side. That is actually what's supposed to happen, because as these gas clouds and stars, etc., approach a black hole, they swirl around it at very high velocities and experience what is known as the Doppler effect. So this is the same effect as when you hear a siren and it's approaching you slightly higher pitched and also louder, and as the ambulance, for example, is receding, or is going away from you, then the pitch and the sound go down a little bit. So this is what's happening. In this particular example, the gas is swirling out of this board in this region and going into the board in this region, therefore making one side of this ring brighter than the other. Okay? So this is what we're looking for, the ultimate signature of an event horizon. Now, this is perfectly fine if you're just doing a theoretical calculation and you say, this is what black holes should look like. It is a whole other beast when you want to go out and look for this in the sky, for black holes that you know, and you actually want to see if there is complete blackness here and this bright ring, brighter on one side than the other. In order to do that, you actually have to account for all the astrophysical complications. How is this gas really moving? Where is the light coming from? Is anything obscuring it? Am I sure that if I point a telescope to this black hole, there is nothing between me and this black hole that's going to absorb this away and get in the way of my experiment? So for the past 10 or so years, we've been developing more and more sophisticated models, astrophysical models, of what this environment around the black hole actually looks like in order to get ready for this experiment that I'm going to describe to you. So one thing that we did, because these computations are so expensive in the sense that on a normal computer they would take days to run, we've looked for ways of accelerating how we compute what these astrophysical systems do. What does the environment of a black hole really look like? So what I'm going to show you is not an animation, but a movie of a postdoctoral fellow that was in my group. This is his hand. This is his laptop. The laptop has a processor called a GPU, the graphics processor unit, as opposed to the normal CPUs that we have everywhere. Actually, nowadays we have GPUs everywhere too. On your phone you have it. That's what controls the display. On a computer you have it. Most devices right now also come with GPUs. And what GPUs do is compute many processes at the same time. So they speed up what we are able to do very, very drastically. So one other thing that I should point out, this is a leap motion device. So instead of actually typing commands into his computer and running a code in real time that calculates what light around the black hole does, he's going to control this whole thing with his hand. So there we go. He's initializing it and running all general relativistic equations forward in real time. He's solving actual physics equations, shooting 1 million photons through this black hole at the center. When he zooms in like that, you see that a lot of light got trapped around it. These are the ones that were gravitationally lensed and got kind of trapped by it. He's running it forward, and what the heck, why not run time backwards? Because we can actually run it on the computer. So when he zooms all out, what you will see in the original wall of photons that were this light that was shot towards the black hole is that some of it actually got trapped, some of it got delayed, and it left that hole in what was a sheet of light that was going towards the black hole. So that right there is your shadow. Now this is fun, obviously, but this is what we can do on a single laptop, and it's not enough if you want to explore really all the possibilities of what happens around the black hole, as I said, to get ready for this worldwide experiment. So with a little help from the National Science Foundation at the University of Arizona, we actually built a whole cluster of these GPUs so that we could still play games, but on a much larger scale. Gaming on steroids is what we like to call it. Incidentally, when we did this, we found out that there is a green 500 list. I had never heard of it before, but I was proud to be on it, which actually ranks clusters, computer clusters around the world for their energy efficiency. So it's not enough to have a lot of flops on it. It is how energy efficient you can make those computations. So we were number 7 momentarily on that list. As you know, these things change on a weekly to monthly basis. So we went a step further, and we really wanted to understand the structures in the 3-dimensional simulations that we were looking at and really map it to the light that we hope to observe with the Event Horizon Telescope. So we also imported all of these calculations to a platform called the HoloLens. There are many virtual reality platforms like this. The only difference is that these, again, are actual physics calculations that we're performing. Okay, so now I want to take a few minutes and tell you more about why we're doing this. I mean, of course it's fun. Of course we all would be excited to take a picture of a black hole, but physics-wise, is there another reason? What I described to you in the beginning of this talk was how Newton's theory of gravity worked great for a couple of centuries until we found a place where it didn't work anymore. It wasn't compatible with another theory. It wasn't compatible with data. And that gave us the impetus to reformulate our thinking and come up with a whole new physics theory. So we keep doing this as physicists. We are kind of masochistic that way, if you will. We find something, we test it, we are happy, and then we start getting itchy, and we're like, well, does it actually work in this limit or in that limit? So one of the reasons we do this is, do our theories of physics fail somewhere? In this particular case, of course, does general relativity fail somewhere? Do we expect it to fail? Well, we kind of do, because just like Newton's theory wasn't compatible with special relativity, general relativity is not compatible with quantum mechanics, another pillar of physics. So we know that at some level it has to fail. What we don't know is if it's going to fail around black holes. In the black hole formation process, is there something we're missing? Does it really form an event horizon? We also, as I said, look for contradictions. So what quantum mechanics predicts and what general relativity predicts are a little bit different. So can we find signatures of that contradiction. And as astrophysicists, we have a belief, if you will, or a framework that what we can test and understand here actually works elsewhere in the universe, that the laws of physics are universal. So black holes are part of the universe. Do we have any evidence that when the gravitational fields are, the gravitational settings are as strong as what's around the black hole, it's not Mercury and Sun anymore. It's not even neutron stars anymore. It's really a different beast. So do we have evidence that our theories work there? So these are the reasons why we go looking for signature of an event horizon, taking a picture of a black hole and measuring how big it is, as you will see shortly. But let's admit it, the real reason why we're doing this is because we want to know if Hollywood got this right. You've seen Interstellar. You've seen claims that this was a physically correct image. Let's go and see if they did it right. Well, even now, with what you've heard, you should be able to tell me it's not completely correct because they drew it symmetric on both sides. They should have drawn it brighter on one side and less bright on the other. But we'll forgive them that. Did they get the rest right? Okay, so this is the framework in which we're going to go look for black holes. And now we need targets. We need to find black holes in the sky for which we can perform this experiment of snapping a picture of their event horizon with the bright ring around it. Now, you have to be pretty careful in how you're going to do this, because as I said, first of all, you want to be able to see all the way down to the black hole. I'm going to show you in a minute an actual physical calculation turned into a simulation of what the gas clouds at the center of our galaxy look like. These are surrounding the black hole that is at the center of our galaxy. So if you looked at a long wavelength, like a long radio wavelength, it would actually obscure the black hole. But if you cranked up the wavelength and started looking at it at a millimeter, what you would see is all that crud around it disappearing, and this shadow and the bright ring appearing right at that wavelength. So we want our atmosphere to be transparent. We're going to turn a telescope to it, and we would like to be able to get the signal. We would like the galaxy to be transparent. We don't want stuff that's between us and the black hole to absorb that light. And what I call this plasma around the black hole, all that gas cloud. Let me show it one more time. So if you look at the wrong wavelength, this is the opaque clouds that you would see, this plasma. But as I crank up the wavelength of light at which I'm making this observation, you will see that the center is appearing just as we want it to. So you have to pick the wavelength right in order to fulfill all of these conditions. Luckily, there is such a wavelength. 1 millimeter goes through our atmosphere, goes through the galaxy, and allows us to see all the way down to the event horizon of our galactic center black hole. So I will admit that this is an experiment that's about 20 years in the making. It is a very challenging task, not just because of all the theoretical simulations that I described. Setting up the experiment itself is very challenging. And as I mentioned, you have to pick your targets carefully. This is what our galactic center looks like in radio wavelengths. There are all of these structures and supernova remnants, etc. But what we're interested in is this bright source, Sagittarius A star, which is the glowing of the gas that's around the 4 million solar mass black hole that's at the center of our galaxy. We call it Sagittarius A star. So our best target, because it's the biggest in the sky, right? We want to take a picture of something, you need to be able to resolve it. So you want you're looking for the biggest thing that's in the sky, even though it's not the closest black hole, because it's more massive, it's the biggest in the sky. It's Sagittarius A star. Well, it is really, really big. Its shadow size is comparable to a donut on the moon. That's how big it's going to get. This is the closest big black hole that we have. So when I say we're trying to take a picture of this shadow and the bright ring around it, think of your normal morning donut, the one with the hole in the middle. Take it to the moon, and then come back and try to snap a picture of it. That's what we're trying to do. So for those of you who are a little bit more technical in the audience, it's 50 micro arc seconds in the sky, okay? So it requires just an Earth-sized telescope to be able to resolve it, nothing more. Luckily, we can do it if we build a telescope that's as big as the Earth. You can go to the National Science Foundation and ask for a huge computer cluster, and they may say yes. If you go to them and say, I want a radio dish that's as big as the Earth, they're going to say no. So what's the next best thing? It is a technique called interferometry. So you pretend that you have an Earth-sized telescope by combining the various telescopes around the world and making them behave collectively. So having them talk to each other in a way that makes the whole experiment seem like you're observing with a single telescope. How do you do that? This is our black hole in the sky, the picture that we're trying to snap. It's emitting all this light. It's reaching us on Earth. Let's say that I put one radio telescope here, one part of the Earth, and another here on another part of the Earth. This is atmospheric noise. Let's not worry about it. The signal will reach this telescope, and sometime later, it will also reach this telescope. Now, if I record the signal with extreme fidelity, so every wave, incoming wave, if I time tag it with a hydrogen maser clock, something extremely precise, more than a billionth of a second time tagging. And I do the same here. Then I can take the hard drive that I used here and the hard drive that I used here with this extremely precise recording, send it to a processing center, which we call a correlator, and then add these up. And obviously, this signal reached this telescope a little bit later. So shift it in time until I find the exact same pattern. And then I can combine the signals and actually have information as if my telescope dish went from here all the way here. I'm not going to collect that much light, but I'm going to have the resolution that corresponds to that separation between the telescopes, as if my lens was that big. So we embarked on this. We started putting telescopes around the world or using existing telescopes and adding this interferometry capability that I just told you about. This is the Event Horizon Telescope Array. That's the official name of the project. These are the 9 stations that make up the array. LMT in Mexico, SMT in Arizona, SMA and JCMT in Hawaii, ALMA and APEX in the Atacama Desert in Chile, SPT, the South Pole Telescope, one of our most important telescopes because it just provides such a long distance between itself and the other telescopes that it really spans the Earth and makes it look like we have this Earth-sized dish, and 2 in the Alps. So it took about 15 years to not only get this collaboration together and do the social work that is necessary to get several hundred people from around the world to work together. But of course, not all of these stations had the necessary tools, so we had to outfit them. And the way it works now is that when we look at the Earth from our galactic center, as the Earth rotates, pairs and triplets and quadruplets of these telescopes are able to simultaneously observe this black hole at the center of our galaxy and record data. So we actually use the rotation of the Earth to be able to get even more information than if these were just single points in the, on Earth. So I said we had to outfit these telescopes. This is a typical millimeter receiver covered in gold. And that's not because we like shiny things, although we do like shiny things. It's because gold has wonderful conducting properties, and we have to keep telescopes cool to be able to reduce noise at a millimeter. So this is from Dan Maroney's lab, a colleague in the collaboration. This particular instrument went on the South Pole telescope. The dish was there, but the millimeter observing capabilities and the connection of that signal with 8 other stations across the Earth was not there, so that had to be built. So Dan took that down, along with his graduate student, who's down here. That's how we treat grad students. This purple cover that you see went on that gold receiver, and this is the South Pole telescope dish. So they took it down last year during the southern summer, and actually installed it. And then we got to test it with a few other telescopes. I'll just show you one. You don't have to exactly figure out what this is saying, but this particular test was done between the Apex in the Atacama Desert in Chile and the South Pole telescope. They looked at a source simultaneously, at Sagittarius A star simultaneously. And what this says right here, this yellow line, that curve that you see, is that when they did this shifting in time and overlapping, it gave a booming signal. So when this tandem observation works, this is what the signal should look like, and that's exactly what we got. And we did this for many pairs of telescopes in advance of the full array observations, which we carried out earlier this year. So April was a very exciting time. 8 out of the 9 telescopes, all but one in the Alps, was ready. We had cooperation from everybody who operated these telescopes. We sent collaboration members to each one of these places, and we got to look at not only Sagittarius A star, our main target at the center of our galaxy, but we also got to look at M87, which is a nearby galaxy with a huge black hole. So even though it's 1,000 times farther away than our galactic center, its black hole is almost 1,000 times as big as ours. So it just makes up for that lost distance, and it's almost as big as Sagittarius A star. This is from David Sanchez, one of our collaborators, who was at the LMT and sent us this picture. You can probably see, this is not working, that's all right. You can probably see the Milky Way in the back because we are looking at the galactic center. This is what LMT looked like as it was pointed towards the center of our galaxy. Now, it's a bit of a nightmare to coordinate 8 or 9 different locations literally around the Earth, all of which might have weather, they might have technical issues, they might have personnel issues. Is everybody ready to do this observing on a given night? So we set up central command at Harvard University at the New Black Hole Initiative, where we all were, where the leadership of the collaboration was. And you can probably count the number of screens here. And we weren't, the reason why we had so many was that we had weather stations from each of these locations. How is the weather in the South Pole? How is the weather in Chile? How is the weather in Arizona? So we had to keep track of all of that, as well as the technical readiness, in order to decide on a given night whether we're going to carry out the observations or not. We had a 10-night stretch, out of which we could observe for 5 full nights, and we could go rotate through our targets. We were extremely lucky. Of course, all of this technology get summarized on a whiteboard. This is ultimately how we made the decisions. The list of telescopes, if we like the weather, if they are technically ready, how does the night look? Because we really need to wait for sunset to carry out the observations. And what's the multi-day outlook like? If we don't use this given night, does tomorrow look better or worse? Can we make a prediction? So it's worse than the stock market. We really all got gray hair trying to do this. But ultimately, we got 5 beautiful nights of observations and recorded several petabytes of data. It's an unbelievable amount of data recorded in that time frame. So this is what our schedules looked like. As I said, early April. This is Sagittarius A star. Now, not only were we able to look at things with the Event Horizon Telescope, but because all other telescopes, whether this is X-rays or infrared telescopes, or a lot of them, Chandra, Swift, optical telescopes around the Earth, because they knew we were looking at the source, they were kind enough to schedule observations to look simultaneously to help us out with data interpretation. It always helps to have, of course, data coming at different wavelengths to see what the weather around the black hole is. It's not enough to know what the weather around, weather in our atmosphere is like. Is everything doing well? So this is how we looked at Sagittarius A star with the series of telescopes and the other big black hole that I mentioned, M87. So unfortunately, I don't have a picture to show you because we are in the process of combining, correlating, and analyzing all of these data. It will take several months for a variety of reasons. I said the amount of data is extremely large, so it really takes physically a lot of time to just combine them. The other reason is that the South Pole is now at a winter state, so no flights in or out. So we don't even have the disks from the South Pole yet. They will arrive in October. So realistically, we're looking at the end of the year for the image. But for now, let me just tell you what we expect to see. All of those very expensive computer simulations that take into account the motion of the gas, what the light is doing, is it going to be obscured, is it not going to be obscured. So this is now in a movie form, what we expect to see if we can do a time-dependent image. Or if we now combine it all together, this is what the computer simulation without instrumental and atmospheric, etc. effects are. And we hope to be able to reconstruct it after taking all of that into account to the image on the right. So both of these are simulations, obviously. But this one is just the theoretical simulation of combined data. This one now says, OK, I'm going to take into account everything that happens during an observation, including combining it with interferometric data. This is what we hope to be able to create by the end of the year. So I personally am very excited that we might actually get to see a picture of a black hole, as small as it is in the sky. But I started by saying that as physicists, we are always interested in pushing the boundaries of our theories and seeing if it actually works. So in particular, we want to see if general relativity's prediction of a black hole, whether the shadow is there, whether that bright ring around it is there, is correct. We want to go one step further. We want to say if that shadow is there, we know exactly how far away this black hole is at the center of our galaxy. We know exactly how massive it is. So we should not only see a shadow, we should see a shadow of a very particular size. There is no wiggle room. It has to be 50 microarcseconds across. So we are hoping to analyze an image like this and measure its diameter with all sorts of fancy image reconstruction techniques that I'm absolutely not going to get into. But basically, what we say is that if GR is right, from the left side of the image to the right side of the image, the size of that black hole shadow has to be a certain number. There's 4% uncertainty in that number. And our experimental uncertainties are going to be of that order. So we are going to be able to say not only whether there's an event horizon, but if it's like the one that is predicted by general relativity. So I'm just going to wrap up here. Hopefully, by the end of the year, we will have all of these results out. And stay tuned. Thank you.
Thank you for a wonderful talk.
Thank you.
We have time for questions.
So you mentioned that one side of the theoretical ring is going to be brighter than the other.
Correct.
Because the gas cloud is going to be rotating on some axis.
Right.
But it will only be brighter on one side if the axis of its rotation is perpendicular to the plane that we're viewing it, correct? So shouldn't we be looking for a black hole whose gas cloud has an axis of rotation parallel so that there is no lopsided ring?
Okay, that's a very good question. Let me answer it in a variety of ways. So the question was, does this left-right asymmetry in the brightness persist if the black hole is pointed, if the axis of the black hole is pointed towards us versus away from us in whatever plane? And should we be looking for one where this right-left asymmetry doesn't exist? So let me answer the second one first. We don't have that many options. We're working with what nature has given us. As I said, the biggest one in the sky, the closest big one, is a donut on the moon. So we're just going to work with what we have. But there's actually a better answer, which is that the gas cloud is not in a torus around it. It's actually more puffy, and the entire thing is rotating. So unless we're in the very unlikely situation where we're looking exactly down the rotation axis of this gas disk, the left-right asymmetry will persist. It's not a big deal. In the slide that was just before this one, even though only part of the image is there, we have so many image reconstruction techniques that we can see the shadow, we can measure its size. So it's actually not detrimental to the experiment that we have this crescent as opposed to a ring.
Are black holes usually accreting mass at a rate that gives you enough luminosity to do this experiment?
Great question. Are black holes accreting enough mass that they radiate enough luminosity for us to be doing this experiment? Black holes typically do interact with their environments and do produce copious amounts of gas. They do go through quiescent stages where not much is happening, but all the black holes that we know in the sky, we know about them because they are accreting and because they are bright enough. There's actually a counter concern. If they're accreting too much mass, that movie that I showed you where you can zoom in, find just the right wavelength that you can go through all that stuff and see down, you won't be able to do that. So if we were looking at a black hole that was accreting at a much higher rate, we wouldn't be able to do this experiment. Our galactic center black hole, Sagittarius A star, is pretty wimpy, I'm sorry to say. First of all, it's only 4 million solar masses, like 4 million times the mass of our sun. What black hole is that small? As opposed to M87's a billion solar mass black hole. And second, there doesn't seem to be too much going around it. So it's really a Goldilocks situation. It is accreting. There is light around it. We know from previous observations. So we know we will be able to do this experiment. But we think it's not so much that it's going to obscure our way into the horizon.
I'm not a scientist, but I have always thought that there was an undercurrent of feeling in the science community that eventually everything will be devoured in a black hole. And is that why you're studying all this? I mean, isn't isn't there a belief that the universe came out of a black hole and that now we're all going back towards the black hole?
So I think there is some similarity between a black hole and the beginning of the universe in that there is a singularity, an infinity in the energy density that is at the beginning of the universe and in a black hole. But the similarity ends there. Black holes are very powerful for things that are in their immediate vicinity, and they can interact with them and pull them in, pull gas in, pull light in. But their sphere of influence is really small. I mean, if it wasn't, we wouldn't be looking for a shadow that is so small, even though it's a pretty big black hole. So you really have to get pretty close to it to know that there's a black hole there, or just like we're doing, look at the light that's coming out of it. So there is no thought in the scientific community that we will end up in a black hole, that the universe will end up in a black hole. In fact, the universe's expansion is happening at an accelerating rate. So pretty soon we won't know that there are many galaxies around us, pretty soon being a few billion-ish years. We won't know that many black holes, anything other than what's in our galaxy. So from that point of view, we are safe.
When you started, you were explaining gravity, and as you and your fellow scientists understand it, you said it was a geometric, the curvature of space due to mass. Do you still look for I haven't heard of it lately, graviton particle that they think has the force that creates that? Is that
Yes.
still a thing you look for?
Yes. So this is one of the things that I didn't get into very much. We do try to come up with a quantum formulation of gravity, because as much as we love our geometric theory, all other theories are quantum mechanical. So these are forces mediated by particles. And the one that is supposed to be mediating the gravitational force is called the graviton. So yes, there are different types of experiments that look for the graviton itself, its effect on the structure of the universe. And there is a chance that if the particular quantum theory of gravity is effective enough on the scales that we're looking at, maybe we'll see a deviation at the horizon scale.
But you don't have any idea what that particle is?
No. We have an upper limit on its mass. So we know that it has to have a mass that's smaller than something. That's all we know.
You mentioned that there's a 4% wiggle room in
Right.
the size.
In the size. Mm-hmm.
Where does this 4% come from? Like, what are the uncertainties?
Very good question. So I mentioned there is a 4% wiggle room for GR to be right. And I didn't say that, of course, but where does it come from? So the most that we know about the black hole at the center of our galaxy comes from following the orbits of stars that go around this black hole. Nowhere near the scales that we're looking at. These are stars that are quite a bit farther away, but they make complete orbits around it. And there are two groups in the world who have been following those stars literally for about 20, 25 years. And because of their exquisite measurements, we see full orbits of these stars. And just like we know what the mass of our sun is by looking at planetary orbits, we know what the mass of that black hole is and the distance of that black hole is by looking at these stellar orbits around it. So that is what that constraint comes from.
When and where can we see the final answer to this next winter? Next spring? Where do we go look for chapter 2?
So if this is the picture, it will be everywhere. You won't have to look for it. If this is not the picture and we see something like cruddy and that we can't make out a shadow, maybe we'll keep quiet until the next observations.
Thank you.
Simple layman's question.
Sagittarius A imply that it is in the constellation Sagittarius?
Yes, it does. So if you want to know where the center of our galaxy is, look for the constellation Sagittarius. That's one of the very few that I can identify in the sky because I'm not an observational astronomer. But yes, look in the direction of Sagittarius, and that's where this black hole
And
is.
A designates that that's the brightest object in the
It's the first radio source that was found in that direction, correct? Yes. But it is 26,000 light years away. So when I say look in the direction of Sagittarius, the constellation, don't worry, it's really nowhere near us.
So beyond this photo or this simulation of this asymmetrical ring, what are some other examples of potential results you might be excited about getting from this experiment?
Okay, very good question. Yes, of course. So obviously our primary scientific goal is to see if that shadow is there, if there is some signature of the event horizon, and how big it is. What else can this experiment do? What are some other scientific questions that we might be able to answer? So I focus primarily on Sagittarius A star because it is what this experiment is mostly about. But M87, for example, has jet structures that are not just coming out of the black hole, but they are so large and so powerful that you can see it on galaxy scale. So when Hubble Space Telescope or Chandra or any one of the radio telescopes snaps a galaxy-sized picture of M87, you see these very powerful jets coming out of the black hole. Our galactic center black hole doesn't have it. And we don't know what the difference is. We don't think it's the mass of the two that is causing this difference. We think something about their environments, for example, how fast the black hole is spinning. Ours might not be spinning, and M87 might be. We're not sure, but that's one of the forefront thoughts about it. So we can answer questions such as what forms jets around the black hole? Can we measure the spins of black holes? How do they affect their environment? So we're going to get the highest resolution image ever of a black hole interacting with its environment. And we know that while galaxies form in the universe, their central black holes play a huge role in shaping what those galaxies look like. So we're hoping to get some insight into that. So a lot of secondary questions.
Will the James Webb, which is going up about a year and a half from now, will it, because it's 6.5 times the Hubble surface area, so would it be able to help define by a factor of 6 times better resolution of all of this stuff?
That's a very good question.
And also, will it be able to monitor with greater definity, excuse me, the fineness of the wavelengths that it is programmed to pick up?
So different science questions require different telescopes to be answered. I described, for example, how we had to find the right wavelength in order to do this experiment. So when we look towards the center of our galaxy, optical telescopes aren't very helpful because there's a lot of absorption of light, of optical light, between us and the galactic center. James Webb is an infrared telescope, so even though it is the successor to Hubble, and even though it is 6 times bigger, etc., it also is a slightly different wavelength because it's designed to look at somewhat different objects, like newly forming stars and galaxies, looking further back in time. So it's not going to help us greatly with the galactic center, but it certainly will look at M87 and will look at other black holes in the nearby universe and tell us a little bit more about their infrared properties, which we can then fold in.
Please.
Yeah.
Regard to the gas spinning around the black hole, is the speed relativistic speeds going on there?
Yes, they are.
That's why it gets brighter with the higher, because a normal Doppler shift to me doesn't increase amplitude, just a frequency shift.
Every Doppler shift has an amplitude increase that goes along with it. But you're absolutely right that as the speed goes up and reaches relativistic speeds, that effect is much, much larger than what we are used to in daily life. So yes, the gas around the black hole does reach relativistic speeds. That's why it glows so much too. That's part of the reason. And that's why this Doppler unevenness between the two sides is so pronounced. Yeah.
Please.
When you refer to the axis, is that axis relative to the shape of our galaxy? And are you implying a shape to the black hole as a cylindric or what?
So there are three axes that we could be talking about. One is the spin axis of the black hole. So if a black hole is not spinning, it's spherically symmetric. But if it is spinning, the space-time around it actually does have an axis. There is also the axis of the stars that are in orbit around the black hole that are feeding it gas. So what I was referring to was not necessarily the black hole spin axis, but the spin axis of the gas that is swirling around it. Now, logic tells us that if the black hole grows by accreting this, by absorbing this gas that is in this disk around it, that its spin axis and the spin axis of the stars will align at some point, but we don't know for sure. There is also the spin axis of the galaxy, which may or may not be in the direction of the stars or the black hole. So what I specifically referred to was the spin axis of the gas that is circling around the black hole and is going into it. But it is possible that that is aligned with the spin of the galaxy, and it is also possible that it's aligned with the spin of the black hole.
You asked the question.
Yeah.
Yes.
I was just wondering if you, in relation to measuring gravitational waves, where we are with that research.
So gravitational waves is definitely another wonderful way of going after our theory of gravity, whether it's complete, whether black holes exist. Gravitational waves look at not single black holes, but black holes and neutron stars that are orbiting around one another, and they lose energy by emitting these gravitational waves. Where we are is that the LIGO collaboration has detected so far the in-spiral and merger of 3 pairs of black holes, which is fantastic. So the minimum that we can say is that the loss of gravitational waves from those systems do look like they are coming from black holes, and the masses look like they're coming from black holes. But it's a very different test of general relativity than what we are carrying out. So it's complementary and will inform one another.
They have been measured, though?
They can from the signals that they have gotten so far, those 3 events, they can find the masses of the objects that coalesced, but they can't say whether they are one-to-one described by general relativity. Not enough signal yet.
I think we'll take one last question from the young lady over here.
Based off of our understanding so far, what would be the best way to image a black hole? What we're doing now, or would there be a more optimal way?
Wavelength-wise, I think what we are doing now is optimal, but we are limited by the land mass and where those telescopes are on Earth. So it may sound slightly crazy, but ultimately we would want to put a radio telescope in orbit around the Earth. That will, of course, increase the resolution, so we won't be limited to the diameter of the Earth. We will actually get a finer detailed image if we are at some point able to put a 10-meter dish in orbit. We are also thinking about the moon, but there is no advantage really to putting it on the moon as opposed to just in orbit.
Telescope give you better imaging than a radio telescope?
That's a great question. So when I showed you the list of all the telescopes that were looking at it, when we were looking at it, Chandra X-ray telescope was among them. And Chandra has been really crucial in refining our understanding of the galactic center black hole. For example, it sees some flaring activity. And so we know that there is a little bit of activity, weather variability in that gas around the black hole. Chandra helps us pin it down along with other telescopes. So it depends a little bit on what the mass going onto that black hole looks like. There are some cases in which X-rays might be a better way, but for the most part, the radio observations that we're doing right now, as far as resolution, are the best.
Thank you.
Thank you.